Hi class, we are now on chapter 0.6. We are going to be dealing with enthalpy. Enthalpy was something that you learned about in chapter 11, specifically during calorimetry. We have just covered calorimetry in the previous section, but that was at constant volume in an isolated system. This is now constant pressure, meaning open environment, open to the atmospheric pressure. So enthalpy, with an H, most chemical reactions are performed in open systems, with an exchange of both heat and work between the systems and surroundings. We are really not interested when we're doing these reactions in work, because the amount of work really isn't going to be enough for whatever purpose we need. We're interested in the flow of heat and how much of that flow of heat. So this is where enthalpy will come in. So if we look at this equation here, here's enthalpy is equal to internal energy plus pressure and volume. Enthalpy is a state function. That means that it doesn't matter how you get from point A to point B. We only care about the initial and final conditions. The enthalpy change of a reaction is the heat involved in a reaction at constant pressure. So eventually on the next page, I'm going to show you how it goes from this to just this, where we only care about the heat, and then that would be the enthalpy change. Usually enthalpy, a change in enthalpy and a change in internal energy are similar in values. The difference is when the reactions produce large quantities of gas, and that has to do with it going into the surroundings. But in this case, for this course, we're not going to really worry about that. All right, so how do we get from one to the other? Well, if we set it up with a change in all, we have a change in enthalpy, change in internal energy, and then we have our pressure with a change of volume. Remember, internal energy is equal to Q plus W. So if we substitute the E and put the heat plus the work, well, this also represents work with the negative sign. So if we plug these all in, the W's will cancel out, and it leaves us with enthalpy, which is equal to heat at constant pressure. Okay, endothermic and exothermic reactions. When enthalpy, the change in enthalpy provides a positive number, that's an endothermic reaction. Heat is being absorbed from the system. When enthalpy is negative, that is an exothermic reaction. That means that heat is being given off into the surroundings. And if you've ever had any contact with a heat pack or cold pack, then you'll understand exactly what I'm talking about. Your hands will get cold with a cold pack, and a hot pack will release heat into your hands. So summarizing enthalpy, the value of delta H for a chemical reaction is the amount of heat absorbed or evolved under conditions of constant pressure. So unlike last section where that was constant volume, now we're at constant pressure. An endothermic reaction has a positive delta H value, and an exothermic has a negative delta H value, which both of these, remember, is also still equal to Q. Constant pressure calorimetry is commonly, if we had been in person, or if you were able to do lab in person, I don't really know the situation for most of my students for 111, you would have used styrofoam cups, and you would have done this with these styrofoam cups. Why? Because the styrofoam cups pretty much handle constant pressure calorimetry very well, and they do minimize the heat transfer because of how the cups are insulated, but they're not sealed, so everything's still open to atmospheric pressure. So this allows us to make very easy measurements of Q at constant pressure, for any heat transfer using this aqueous solutions, which is water. All right, and that's what it looks like. That's what you would have gotten in class. You would have had two styrofoam cups. They would have been stacked upon each other. You would have had a lid, and you would have had a thermometer, and not a stir bar. You would have used the thermometer. Very fancy, but honestly, it gets the job done very easily. So we had another section where we looked at specific heat, and I didn't give enough, I think, examples in that. And since this is constant pressure, at constant pressure, I am putting these also here. So basically what I'm trying to say without being tongue-tied is I have examples to calculations that I felt that some of this should have been under when we covered specific heat, but it also is under enthalpy. So calculate the specific heat of water if 83.68 joules is required to raise the temperature of 4 grams of water by 5 degrees. So remember, this is Q, we're looking at enthalpy, but this is also under specific heat. So this, I'm just breaking it down on one page. So this should look familiar. Q is heat, mass. C here should be, I told you, some sections, some books, they all changes from C to big C, some label it SH, they all mean the same thing. Is specific heat for that material, and then the change in temperature. So this is asking for the specific heat of water. If we needed to, if 83.68 joules, having one unit should tell you this is Q, is required to raise the temperature 4 grams with the mass of 4 grams of water by 5 degrees. So everything's pretty much given to you here. You just have to solve for the specific heat, which is C. So you isolate C away, rearrange everything, and the specific heat of water is 4.184 joules over grams Celsius. And specific heat has 3 units, so that matches. Okay, so calculate the final temperature after 1485 joules of energy is added to 16.7 grams of water at 23.4. So this is an entirely different problem. This is asking for the final temperature, where we would use delta T, and sometimes the problem would be given to you, the temperature change would already be given, but most of the time you are given both initial and final conditions of temperature, and you would have to solve for something else. But in this case, you have to solve for the final temperature. So you set it up with all the information that you have, and in this case we're going to rearrange it for delta T. So we have Q, our mass, and our specific heat. So rearrange the equation, and once we do and we plug everything in, we have 21.3 degrees Celsius. However, that is not all the information. We're not done here. So this is only giving a temperature, but that's not the answer to the problem. You have to really understand what the problem is asking. This problem is asking for the final temperature. So if we look at here, we have a temperature here, and now we have another temperature, but we still don't have the final temperature. So we need to take a look here. This might make more sense. So we solve for the problem. We're given 21.3 degrees Celsius. Now we need to determine the final temperature, because remember, if you look here, all that is the change in temperature. This number here is the change in temperature, but it's not the final temperature. We need to use the final temperature, which if we normally would set it up would be delta T equals T final minus T initial. But if we isolate T final, it comes out looking like this, and we plug everything in, and our final temperature is 44.7 degrees Celsius. All right, a 25 gram sample of a metal at 87.7 degrees Celsius is placed in 37.4 grams of water at 10.3 degrees Celsius, and the final temperature of the system is 15.4 degrees Celsius. Calculate the specific heat of the metal. This seems like a lot of information in just a few sentences, and it is. It's not that difficult though. You just need to first isolate what values are going with the sample of a metal and which values are going with the water. And once you can set this up, remember that when we have something, for instance, if you put hot metal into water, the heat that's been transferred, the heat will be transferred from the hot metal to the water. So one's going to gain and one's going to lose. And we can set these up to each other and then make them both equal to 0. So you can make this as an equal sign, and you can make this equal, or you can just cheat and put it like this. All right, so the heat lost by the metal is equal to the heat absorbed by the water. Now, we have everything. All you would need to do now is pick everything out and plug it in. However, let's start at the temperature of, we have a temperature of the water and we have the temperature of the metal. So the temperature of the water, we have a final and final minus initial, and it is 5.1 degrees Celsius. Same thing we can do for the water. We have 15.4 degrees Celsius minus 87.7 degrees Celsius. And that means that for the metal, we have negative 72.3 degrees Celsius. So we finished doing our math for that one, and let's move on. Okay, so once we have the math for the temperature change for both the water and the metal, we can plug everything in. So if you make these equal to each other, or then in this case, then move one over and make it to 0, then you're adding these together. The math could be a little complicated if you're not careful. We're solving for the variable here. So eventually we're going to get down to this. 798.1 joules over 1800 grams per Celsius. And then once we take care of that and reduce it down more, we have 0.44 joules over grams Celsius. So that is the specific heat of the metal. And if you wanted to take it even further to identify the metal, you could look at a chart, and there's 3 possibilities of what this metal could be. But the main thing about this is learn how to isolate what sample goes with the metal, what values go with the metal, what values go with the water. You can set them up against each other and then move one over, plug everything in, and it'll give you whatever it is that you're asking for. This could apply also to final temperature. Any of these variables can be changed. It could be asked for the final temperature of both the metal and the water, which would mean they would have the same temperature in the end. All of these variables can be moved around depending on what the question's being asked. Okay, so calculate the final temperature after 6.8 grams of aluminum at 67.4 degrees Celsius is placed in 195 grams of water at 19.6. So the heat lost by the metal is equal to the heat absorbed by the metal. Is that right? No, that should be water. Sorry. The heat lost by the metal is equal to the heat absorbed by, should be water. Yeah, that doesn't sound right when I said that out loud. Both the metal and the water will have the same final temperature. So this is a perfect example of what I was just saying. You're going to have, in a sense, a same variable, but it's going to end up being on both sides for a little while. So what you do here is you take your information about the temperature and what you have and what you need to solve for. So remember, you have T final. We set it up for the water. So we have our 195 grams water, specific heat of water. We don't have the final temperature, but we have the initial for the water. Same thing goes for the metal. And then basically you just start multiplying and canceling until you get to a specific point that's going to pretty much clear this out. I call it housekeeping. Okay, so then you just keep going till you get your value, and eventually you're going to get a value that's going to get you to 20 degrees Celsius. So the final temperature for both the water and the metal in this was 20 degrees Celsius. Yes, it's time consuming. If you make a mistake, you're going to mess up the whole problem. I've done it. So make sure you take your time and make sure you understand exactly how to set these up and how to keep carrying them through. All right, so the enthalpy of reaction, in the enthalpy change in a chemical reaction is extensive property. That means that it's dependent on how much of that sample you have. The more reactants you use, the larger the enthalpy change. So we calculate the enthalpy change for the number of moles of reactants in the reaction as written. Basically what this is saying is that, see, we have propane gas in the presence of oxygen, so this is a combustion reaction, produces carbon dioxide gas and water vapor. And with this specific coefficients in here, so 1, 5, 3, 4, with this phases, state of matter, produces an enthalpy change of negative 2044 kilojoules. You can read this more than just what you're seeing. So for instance, 1 mole of this gas equals negative 2044 kilojoules. 5 moles of this gas, 5 moles of oxygen equals this. 3 moles of CO2 equals this. 4 moles equals this. So you can pick any of these that you need. This is the coefficients, this is whatever the compound is, and they all equal this. Okay, so consider the following thermochemical equation. We have 2A, and then it ends up producing AA. And the enthalpy, change of enthalpy reaction produces negative 51.0 joules. What is the heat associated with the reaction for 6 moles? This is very easy. This is just a conversion problem. There's nothing more to it. And the qualities are all written here. So what this means is that you have 2A equals this value, and one mole of this equals this. So depending on how you would need to set this up, we would start with 6 moles. So we're going to need this one. The 2 moles of A, because we're not using this one right here, 2 moles of A is equal to negative 51 joules. So if you set that up, that's going to tell you what is the heat that's associated by using 6 moles of A. So this is going to be C. Okay, so relationships involving the change of enthalpy in reaction. So this is the enthalpy change for a specific chemical reaction occurring in stoichiometric quantities. So the change in enthalpy of a reaction is equal to the constant pressure is equal to the heat of the reaction. Now, if we wanted to go further, and it's asking for the enthalpy change per mole, when you're given a problem, if you're given the mass, you change that to mole, or you'll be given more information, and then you just divide it by moles. It's not really that difficult. Look at the units. The units will usually always tell you what you need to do. When a reaction is multiplied by a factor, that enthalpy change of the reaction is also multiplied by that factor. And that has to do with, because again, it's extensive, so the amount that you have affects the value, the final value. So for instance, what this is saying is that, see, we have carbon and we have oxygen gas, but when they come together, they produce CO2. And this is the value for this specific chemical reaction. But what if we multiplied it by 2? Then we have to multiply everything by 2, and that includes the final value of enthalpy change. That also has to be multiplied. We have to adjust everything if an adjustment is made. And what if it's reverse? Same thing. If this is negative and we're reversing the reaction, we have to put a positive. We're going to cover more in this next section, but this is something that should not look new. It should have been covered in chapter 11, and we're just going to go and expand on it.